Hei, alle sammen. Velkommen til Realfagsbiblioteket og dagens og årets siste GeoOnsdag. Mitt navn er Bernt Etzelmøller, og jeg er instituttleder ved Institutt for geofag. I dag er jeg veldig klar for å introdusere førsteamanuensis Matt Domeier. Matt Domeier er en geofysiker med interesser i jordens paleogeografiske utvikling, historien til det geomagnetiske feltet. Han har en bachelor i geologi fra Slippery Rock University i Pennsylvania i 2006, og det er et reelt sted. Han tok en doktorgrad i geofysikk fra University of Michigan i USA i 2012 og flyttet deretter til Oslo. Og her ved UiO har han deltatt i 3 sentre for fremragende forskning. Først PGP, Physics of Geological Processes, som varte til 2013, og deretter på SEED, Center of Earth Evolution and Dynamics, mellom 2013 og 2023, og nå i Center for Planetary Habitability, FAP. Og i dag er han førsteamanuensis ved Institutt for geofag og leder Ivar Giæver Geomagnetisk Laboratorium, som er et nasjonalt infrastruktur. Matt er en av våre fremste forskere og har vunnet flere priser og prestisjetunge forskningsmidler som Young Research Talents Grant fra Norges forskningsråd, et ERC-consolidator-prosjekt dedikert til å forstå det geomagnetiske feltet i Ediacaran-perioden, som vi kanskje hører mer om i dag, og han vant Reusch-medaljen fra Norges geologiske forening og Arne Richters-prisen fra European Geosciences Union. Og dagens foredrag har titelen Reading Earth's Hard Drive. Han snakker norsk, men han holder foredraget på engelsk, og vi gleder oss å se hvordan vi kan lese denne harddisken. Vær så god.
Thank you, Bernd. Can everybody hear me? All right, thanks for coming out. It's a great pleasure to be able to talk a little bit about one of my favorite subjects, the Earth's magnetic field, or more specifically, records of the Earth's magnetic field that are preserved in rocks. And despite the fact that I've been studying the Earth's magnetic field for quite a number of years, I still find the field to be a bit mysterious. And I suspect that many of you also attribute an element of mystery to the force of magnetism and magnetic fields. And I think the reason for that is that we as humans don't have the capacity to physically experience the magnetic field directly. Of course, you can sense the magnetic field indirectly when you're playing with a pair of magnets, but you don't recognize that you're bathing in the magnetic field right now. So all of you out there, me standing up here, we all have magnetic field lines passing through our body at this moment. They're coming through the ceiling, passing through all of you at an angle of about 70 degrees down, going through the floor. And you've been in the magnetic field your entire lives, except for those of you that have visited our lab in the basement of the ZEB building where we have some magnetic field-free spaces where we have our instruments. You're welcome to come by and sit in these cages and see if you feel any different. Everyone else has been in the magnetic field their entire lives, and you're going to be in the magnetic field for the rest of your life unless something catastrophic happens. So fingers crossed, we all remain in the magnetic field for the rest of our natural lives. So we can't sense magnetism. We don't appreciate the field, but it's actually carrying with it a lot of really interesting information. There are other organisms that can sense the magnetic field and use it to their advantage, bacteria, for example. And rocks can also sense the magnetic field. And even more importantly, they can preserve information about the magnetic field in the past. And in many ways, you can think about the magnetism of rocks in the same way that you can think about conventional hard drives that are able to store interesting information magnetically. So conventional hard drives are storing information about text documents or images or songs by magnetic signals. And today the talk is going to be about what it is that we can learn from the magnetic signals in rocks, which are also holding precious information. So in a strange way, Earth, at least the outer surface where the temperatures are relatively low, is like a giant hard drive. So it's interesting to think about how it is we can read this and what these signals mean. Okay. So, just to play on this analogy a little bit before I leave it, just because I like this, I'm going to take you first back to my childhood in the mid-1980s. So for the students in the room, you've probably never touched these things unless you visited a museum. But these are all examples of magnetic storage systems, floppy disks, cassette tapes, conventional hard drives. And what these things are all capable of doing is capturing and preserving information, again, text, images, songs, in the form of remnant magnetizations. So just to explain this a little bit, I'm going to have trouble standing still because I'm accustomed to walking around. I won't dwell on this too much, but I just wanted to explain a little bit about how these work in a very simple way. So here we have a cartoon of one of these magnetic storage systems, the read-write center. So at the bottom here, this is just some magnetic tape. It could be from the cassette tape, for example. And we're going to store on this piece of tape, let's say a text document or an image, which we have converted to a binary code, ones and zeros. And we can record those ones and zeros as magnetizations of altering polarity, pointing to the left for a 0, pointing to the right for a 1, for example. And so we can generate magnetizations by passing a small current through this coil, which is going to generate a magnetic field in one sense or the other. And so we can write the information as a string of magnetizations, take the cassette tape out, put it in the drawer, and you can pick it up again in a year's time or 5 years' time, hopefully. And you pass the tape back under this sensor here, and the passage of a magnetic field of a particular sense is going to generate a current of a particular sense. So we can read back these ones and zeros and reconstruct our image or our song. And the magic here is that we can preserve information without an external power source by way of remnant magnetizations. Interestingly enough, we're excited when we managed to discover that our hard drive still has information on it after 10 years. But it turns out that the Earth has been doing something very similar, mindlessly, for billions of years, and is also able to make records or leave records which can persist for billions of years. So the first small step to seeing how this works is recognizing that in some cases we're actually using natural materials in these magnetic storage systems directly. So this is a mineral called maghemite. It's an iron oxide. It's an oxidized form of magnetite, which you may know. It's very common on the Earth's surface. And early cassette tapes were actually using maghemite as the recording mechanism on these tapes. So if minerals can become magnetized, it shouldn't be a surprise that rocks themselves can become magnetized. There's actually a number of different ways that rocks can become magnetized. I'm just going to list off a couple, which are useful for today. One is cooling rocks from high temperature. So here we have a lava, but we could have a dike that's been intruded, for example. And if we blow up some little parcel of this cooling lava, there's going to be some iron oxides in here. And you can imagine that each of these iron oxides, which I've colored dark gray, intrinsically is magnetic, and it has a little compass needle inside, or a little bar magnet. And these are going to be jostling around very vigorously at high temperature, but they're going to spend a little bit more time parallel to the ambient magnetic field, which I've drawn here as these purple arrows. And as the rock cools, these bar magnets are going to start slowing down. They're more and more sluggish, and eventually they get trapped in some orientation. And assuming we don't reheat the rock again, those bar magnets are going to stay trapped in that orientation, potentially for billions of years. And because they spend more time at high temperature, parallel to the magnetic field than not, statistically speaking, we get a very good representation of the ambient field in which these rocks cooled afterwards. So this is called a thermal remnant magnetization. Another very common form of magnetization that we find in the natural world is in sedimentary rocks. And here we have pre-magnetized grains, which could be, for example, disaggregated, weathered and eroded from the lava, sent into the water column. We have little grains of magnetite, little grains of hematite. And as these are raining through the water column, they're going to be physically torqued by the magnetic field into alignment with itself. And this aligning efficiency is not especially high, but if we take a, say, 10 cubic centimeter sample, which is the sample size that we measure in the magnetometers in our lab, you're measuring millions of grains. So statistically speaking, once again, you end up with a very high precision and very high fidelity record of the ambient magnetic field in which these sediments were deposited in. And once again, this magnetization can persist for billions of years. It also doesn't matter what the orientation of the field is. So these processes work equally well irrespective of what you do with the direction of the magnetic field. So we'll discuss in just a few minutes the fact that the magnetic field can reverse. The magnetic field's orientation is also different according to where you are on Earth's surface, which is also a very useful property, which we'll also discuss in a second. It doesn't matter which orientation the magnetic field has. These recording processes are going to work equally well. Okay. So now we've established that rocks can become magnetized. You now know 2 ways that they can get magnetized. Now we're going to talk a little bit about what we can do with this information. And we're going to progress from relatively simple to more complex, both in terms of the measurement techniques, but also the intricacy of the interpretations that are necessarily involved with understanding these data. So what we're actually measuring when we're measuring magnetizations is a vector. So we're measuring a 3-dimensional direction and also a length and intensity of magnetization. So we can decompose this into several different constituent parts, and it turns out we can do different and rather interesting things with these different parts. This is also a very incomplete list. This is just the things that I think are particularly interesting, but there's many other things you can do with paleomagnetic data. So we're going to start just by looking at the directions very crudely, and just considering them to be one of 2 forms, either pointing to the north or pointing to the south. So in many ways, this is going back to the binary code, just treating this magnetic data as 1s and 0s. And we'll find that already just doing this, we're able to date rocks without touching them, which is pretty remarkable. After that, we're going to dwell into a bit more detail into the directions, so measuring the directions a bit more precisely. And that will be able to tell us about the past motions of continents going back billions of years. And finally, we'll look at the length of the magnetization vectors. How intense are the magnetizations? And this is perhaps the most remarkable thing of all, because this provides us a unique window into the deep Earth in the deep past. Okay, so we'll start off with polarity first. So what I'm showing here on the top right is a very simple schematic of Earth's magnetic field. This is the simplest structure. It's called a magnetic dipole. This is the structure you would get if you had a bar magnet aligned parallel to this vertical line, which is the spin axis of the planet. So you're looking at the latitude, longitude graticals here as these dashed lines. The light blue lines are showing you the lines of magnetic force, which are leaving the southern hemisphere, looping around, and returning back into the Earth in the northern hemisphere. The dark blue arrows are showing you the sense of these magnetic field lines. So this is a so-called normal polarity magnetic field. This is the magnetic field that we have on Earth today. And wherever you were standing on this planet, if you had your compass out, it would be pointing to the north. If you were on planet Earth 780,000 years ago with a compass, you would find that your compass was in fact pointing the other direction, pointing to the south. And that's because at that time, the magnetic field was upside down. It had a completely different structure. Well, actually, the structure was the same superficially, but you'll see now the arrows are leaving the northern hemisphere, looping around and going into the southern hemispheres. The magnetic field has been turned upside down. When people first discovered that some rocks appeared to be magnetized anti-parallel to the ambient magnetic field, there was a lot of confusion and discussion. What could be causing these reversed magnetizations? And in the beginning, it wasn't clear if it was due to self-reversals in rocks. It turns out that some rocks are capable of actually acquiring a magnetization which is anti-parallel to the ambient field, or if it was due to true reversals of the magnetic field itself. The solution to this conundrum was to go out and to measure the magnetism of rock samples through multiple stratigraphic sections, and to find stratigraphic successions which were coeval and to compare their magnetostratigraphic profiles. And what we find is that if you go to 2 coeval sections and measure the magnetization, now I'm coloring these different horizons black and white according to a normal or reversed magnetic polarity, that is either pointing to the north or pointing to the south, we find that they correspond, which tells us that this must be a globally synchronous phenomenon. So it's the magnetic field that's reversing. So that's very interesting. The next question, of course, was how often does this happen? And is there some regularity to it? So for that, we have to go out and find some enterprising geochronologists and ask them very politely to date some of the ash layers or lavas that might be in this sequence for which we can get precise numeric ages. And if we do that in enough places, we can build a reference profile. This is the geomagnetic polarity timescale. The numbers are very small, so those of you in the back won't be able to see this. But this is a scale in millions of years, going from 0 on the left to 250 million years ago on the right, and it keeps going, but I've just chopped the bar off because it becomes more uncertain as we go further back in time. This is showing you the state of the magnetic field at various points in time. So the black bars are when the field was normal polarity like today, and there's nothing normal about normal polarity. The field turns out to spend equal amounts of time in both of these states, and the white bars are when the field was in a reverse polarity state. So there's a number of interesting things that you can note here. First of all, it appears that reversals are stochastic. There's no repeating pattern in this geomagnetic polarity timescale. So we have some intervals where there are a lot of reversals, around 140 million years ago, for example, and other intervals where the field appears to be stuck in one polarity for tens of millions of years. These are called supercrons. There were at least 3 of these in the Phanerozoic. And the other thing that's very interesting is because this pattern is not repeating, because it's random, it's a bit like a fingerprint. So that means if you didn't know what the age of this stratigraphic column was, you only had magnetic information. If you had access to this reference column, you could use the sequence that you observed to match back where it came from on the geomagnetic polarity timescale, and with that you can determine the age of the rocks. That, in turn, has been used to great effect, as maybe you're all already aware. Those of you that are not are in for a treat. In the oceans. The reason being that the oceanic crust is very magnetic, and the oceanic crust, when it's being generated along spreading ridges, mid-ocean ridges, it's being magnetized by the process that I introduced in the beginning. The rocks are cooling from a high temperature, so they're acquiring a magnetization, and as the rocks are spreading away from the ridge axis, new rocks are going to be filling in and acquiring a new magnetization. So what that means is if you were to walk from the ridge axis today, where we're acquiring normal polarity magnetizations, and walk in either direction, you would eventually encounter some reversed strip. And if you kept walking, you would eventually encounter another normal polarity strip. So the seafloor is magnetically striped, and we can use these magnetic stripes. Well, I should first mention that we can actually measure these magnetic stripes from the sea surface by towing a magnetometer, an instrument that can measure magnetization, behind a survey vessel. So we can actually image, in a sense, these magnetizations without having to actually physically collect any samples. So you don't have to send a submersible down or a diver down to collect samples from the seafloor, from the oceanic crust. You can measure the magnetization from the sea surface. And these wiggles are showing you where the magnetization is either in the same sense as the magnetic field today or anti-parallel to it. And so we can recognize these normal and reversed magnetizations from the sea surface. And because we can refer back to our handy geomagnetic polarity timescale, we can also identify the age of these stripes. Many of you have already seen a map like this, which is just showing the age of the oceanic crust, but I would just ask you to take a second to reflect on how magical this is. We're using a force of nature that we cannot physically experience directly ourselves, and we're measuring something from the sea surface that's kilometers below, and we're using that to determine the age of 70% of the Earth's surface without touching these rocks. So we have determined the age of 70% of the surface largely without actually having visited it physically. That's kind of remarkable when you think about it. But that's not all we can do with this information. Because we also know how quickly we're progressing between these bars as a function of time, we can also convert this information into spreading rates, and we can match together lines of the same age or stripes of the same age across the mid-ocean ridges, and we can build tectonic models, at least going back to 200 million years using these marine magnetic anomalies, because before that we run out of oceanic lithosphere. So here we're watching this tectonic magnetic tape, if you will. And remember, even though these lines are colored according to age, effectively what we're looking at is just this binary code. It's just ones and zeros, just normally and reversed magnetizations preserved in the oceanic crust. So that's pretty good. So far we've only been thinking about the polarity, just zeros and ones, but we've already been able to date 70% of Earth's surface without touching it, and we've been able to work out the last 200 million years of tectonic motions, all from this tectonic tape that is preserved in the oceanic crust. Okay, but let's move on to directions more specifically. So now we're going to dwell a little bit more into the details of specific directions, rather than just treating them as north or south. So a magnetization, again, is a three-dimensional direction. Here's some arbitrary magnetization direction in green. It's rather complicated to communicate and work with three-dimensional directions directly. So normally we decompose these into two constituent parts. One is the horizontal projection of that 3D direction. That's the gray arrow here. And the angle between that gray arrow and north, we call the declination. That's what you're all accustomed to looking at or measuring when you're out in Østmarka orienteering. What you might not be familiar with is the vertical component of the magnetic field, which we call the inclination. So now this is the angle between the magnetization direction and the horizontal plane. Going back to this diagram, we actually already introduced you to the inclination. So again, these blue lines are showing you the lines of magnetic force leaving the southern hemisphere, looping around, going into the northern hemisphere in a normal polarity field. And the dark blue arrows, again, are showing you the sense. But now I want you to imagine that you're walking along the surface of the Earth here, starting in the South Pole and working your way towards the North Pole. At the South Pole, it would appear as if the magnetic field is coming straight out of the ground. At the North Pole, it would appear, or the magnetic field is, going straight into the ground. If you're somewhere along the equator, the magnetic field is parallel to the surface. It's horizontal and pointing to the north. And at any other latitude, it's going to be progressively changing between vertical and shallow. It turns out that this relationship between inclination and latitude is actually unique. So for any inclination, there is only one latitude, and for any latitude, there's only one inclination. So I don't have any tattoos, but I always thought if I was going to get a tattoo, the dipole formula would look really nice on my forearm. This is the only formula that I'll show. We're not going to dwell into the details. It's a very simple formula. All I want to show you with this is, that, first of all, that it's not a linear relationship. So there's a couple of tangent functions in here. But it's nevertheless a unique relationship. So I is inclination, lambda is latitude. If you put one number in here, you're only going to get one number on the other side. If you put one number here, you're only going to get one number back. So inclination can be mapped to latitude, and latitude can be mapped to inclination uniquely. And that's really important if you remember back to what I said at the beginning, that rocks can record information about the orientation of the magnetic field when they form. So that means if you were to measure the inclination of some old magnetization, some old rock, that tells you the latitude at which that rock formed. So that's a very powerful observation. So to dwell on this point a little bit more, because it's really important, I'm going to use this diagram that's quite old now, 20 years ago, from Trond Torsvik and Robin Cox, but I really like this diagram because of its simplicity. So just to introduce it, on the y-axis we have latitude. On the x-axis we have time in millions of years. Time is being shown in these little white bubbles. And this funny green polygon is the cratonic core of Northern Europe, Baltica. The black silhouette here is Norway, which you probably already recognize, and the white dot is Oslo, of course. So what we're looking at here is Baltica drifting through space and time. And on the sides of this diagram, I have sketched out how the declinations and inclinations in rocks of corresponding age would be expected to change. So if you were to go out to measure the field today, the declination would be approximately 0, more or less north pointing, a small departure due to short-term variations in the magnetic field. And the inclination is 70 degrees down, which is what I mentioned at the beginning. If you were to measure a rock, however, from the Oslo Rift, something that was, say, 300 million years old, you would find that the inclination was actually flat, which tells you that Baltica must have been at the equator at that time, around 300 million years ago. The declination would also tell you that Baltica must have rotated in that time. If you were to go into even earlier time, collecting rocks from the Ordovician or the Cambrian, you would find that the inclinations would be vertically, or close to vertically up, very steeply up, which tells you that Baltica was actually in the southern hemisphere in the early Paleozoic. And again, the declinations would tell you that Baltica has rotated in an azimuthal sense, clockwise and counterclockwise, rather strongly over the course of the last 500 million years. So this is just one continent, but we can do the same exercise on many other continents for the entire Phanerozoic. So if you send out a bunch of enterprising paleomagnetists and give them lots of time, they're collecting rocks of lots of different ages on different continents and doing the same exercise, measuring the magnetization each time, we can start to work out the history of continental drift. So this model is based on generations of paleomagnetic studies from many, many groups, and almost all these blocks are constrained directly by paleomagnetic information, inclinations and declinations coming from rocks of different age. So note that we've gone back more than twice as far as where we stopped with the marine magnetic anomalies, because with the continents we can go back potentially billions of years. I've only gone back to 500 MA because something funny happens in earlier time, which I'm going to mention at the end of the talk. Okay, so those were directions. Now I want to take a stop at paleo-intensities. So paleo-intensity, the length of this magnetization vector, the strength of the magnetization, can tell us something about the strength of the magnetic field itself, which is also varying through time. So here we have two cartoonized planet Earths with a weak field on the left and a strong field on the right. If you were to erupt the same lava flow onto both of these planets, the one on the left would be less strongly magnetized than the one on the right, because the field that it's acquiring a magnetization in is going to be weaker. So if we're measuring the paleo-intensity, we can say something about the evolving strength of the Earth's magnetic field. And this is very interesting because it tells us something about processes that are happening in the deep Earth. The magnetic field is being powered by a machine called the geodynamo, which is basically the spherical bathtub of liquid iron, which is our outer core. This liquid iron is also electrically conductive. And if you're moving a conductor in the presence of a magnetic field, you generate electrical currents. Electrical currents, in turn, generate a magnetic field. Because the fluid flow on the outer core is strongly shaped and regulated by the rotation of the Earth, the electrical currents that are being generated are actually replenishing the magnetic field itself. So the geodynamo is a self-sustaining process. It sounds a bit like a perpetual energy machine. It's not. It's ultimately fueled by heat. But the magnetic field is keeping itself alive by generating electrical currents which are continually replenishing itself. So the heat source, or ultimately the power behind the geodynamo, is convection of the outer core, which is in part driven by heat flowing out of the core. So there's an enormous temperature differential between the outer core and the lowermost mantle, which you can see here designated by this little delta T. So as we're losing heat, we're causing convection in the core, just driven by the heat loss itself. We also have an important secondary component of convection, or secondary contribution to convection, which is coming from compositional buoyancy. So as the outer core is crystallizing, forming the solid inner core, light elements which are in the fluid don't want to go into the crystallizing solid, they're expelled, and so they want to rise through the outer core once they've been liberated. So this is also contributing to the convective system, which is powering the geodynamo, which in turn is responsible for the magnetic field. So changes to the intensity of the magnetic field in turn tell us about changes to these processes happening in the core and in the insulating mantle directly above. So why is that interesting? To make this point, I like using this diagram, which is from Teres Garia. He's a geodynamicist from Zurich in ETH. And he's a numerical modeler, so he's trying to motivate numerical models. Why are numerical models important? So let me set up this diagram a little bit. On the x-axis, on the y-axis, we're looking at depth from the surface to the core. On the x-axis is time, going from present day back to the early days of the Earth. And the circles are meant to show you observational evidence, or areas where we have observational records. So at the origin here, that's the surface at present day, we can make observations of sedimentary systems at work and volcanic systems at work. We can also make observations of the subsurface using remote methods. Seismology, gravity data can tell us about the structure of Earth's interior today. And we also have access to the rock record at the surface, which can tell us things about processes in the deep past, sedimentary systems at work, for example, in the Proterozoic, or volcanic systems in the Paleozoic. But that still leaves an enormous domain, by far the majority of the domain of Earth in terms of space and time, unconstrained by observational evidence. That's the mantle and the core for all points prior to the present. And the reason for this is because, unfortunately, the dinosaurs didn't install seismometers, and the trilobites weren't taking gravity readings. So we have no direct information about the subsurface in the past. Except that's not true, because I just told you on the previous slide that paleo-intensity actually provides us information about processes that are happening in the core, in the mantle, billions of years ago. So that is quite remarkable. Since I'm at the Center for Planetary Habitability, I also want to point out that the magnetic field and the history of the magnetic field is also really important for considerations of the habitability of our own planet as well as the potential habitability of others. So this is our closest star, our friendly neighbor, which is providing us with a lot of our important sources of power. But it's also hurling nasty charged particles at us all the time, which we mostly don't care about because we have a magnetic field which is shielding us from that. And actually, at the moment, we're enjoying the aurora display, which is coming about from the interaction of the sun's charged particles in the magnetic field. But it's an interesting question. What would our planet look like if we didn't have a magnetic field, or if the magnetic field went down? Would we even have an atmosphere, or would the atmosphere have been entirely eroded away by the solar wind? So maybe we would look like Mars. Or perhaps it would just selectively target oxygen in our atmosphere, and we would look more like Venus. In any case, there's a big question mark. What is the role of the magnetic field for our own planetary habitability and also the habitability of other planets? So going back to the history of paleo-intensity, this is a very complicated field, lots of people arguing about their data and the data quality. I'm just showing a cursory overview here of basically all the paleo-intensity data through time. So this is time on the x-axis in millions of years. The y-axis is showing you field strength. Don't worry about the units. And the red dashed line is showing you the present-day field strength for reference. And all these colored symbols, you don't have to worry about the different colors or sizes. It just has to do with data quality. They're showing you estimates of the field's paleo-intensity from the rock record. Note that it goes back remarkably far in time. So there's quite good records back to 3.45 billion years. There's even some points you can see here that extend into the Hadean. These are very controversial. I wouldn't hang your hat on these. But we certainly had a relatively strong field, at least by 3.45 billion years ago. So you might think this is what our field looked like for that entire history, keeping us happy and smiling at the Earth's surface. But I want to zoom in a little bit now on the latest part of the Precambrian, specifically the very last period called the Ediacaran. So we're looking at a very similar panel here that's just been filtered a little bit, but it's, again, paleo-intensity data. So time on the x-axis, strength of the magnetic field on the y-axis. The recent field, again, just for reference, as this pink line. And we can see that there appears to be a monotonous decay from the Archean moving towards the Phanerozoic, with the lowest paleo-intensities ever recorded in the latest Precambrian, in the Ediacaran. So one provocative idea is that just before the Phanerozoic started, the magnetic field either was on its way to its deathbed or maybe even temporarily turned off, because before the Ediacaran, we actually didn't have an inner core. So before that, the magnetic field was entirely powered, the geodynamo was entirely powered by thermally driven convection, and that is becoming increasingly less powerful with time because the core is cooling. So until we had this kick that came from the nucleation of the inner core, the field was getting progressively weaker, and the intensities at the surface were continually dwindling. So I highlight the Ediacaran because this is a particularly interesting period for paleomagnetists. So all three of these data sources that I introduced to you, polarity, the directions, the intensity, all of these systems seem to go haywire in the Ediacaran. So I just talked about the intensity. It appears to have been ultra low. We're looking at, again, the same data. Now I've just turned time around to confuse you, so time is going from left to right. Here is the Ediacaran. This is a bit of a messy panel, but the blue and gray symbols are again showing paleo-intensity. So here is the Ediacaran paleo-intensity records, again lower than anything else we've seen in the Phanerozoic, also lower than anything that we've seen in earlier time. So the Ediacaran field was ultra weak. It also appears to have been hyperactive, reversing remarkably quickly. So the red line here is showing you reversal rates. That's reversals per million years as a function of time. Note that it's a log scale. The Cambrian, or early Cambrian and Ediacaran reversal rates are through the roof, the fastest we've ever seen. But perhaps the most remarkable thing of all are the rates of directional change. So again, we can use magnetic directions to say something about continental drift by measuring the declinations and the inclinations. We talk specifically about Baltica. In purple, I'm showing now the rate of Baltica's motion in centimeters per year that we can infer from its paleomagnetic record. Again, basically that same panel from Trond Torsvik and Robin Cox. But I'm also showing you two other continents which also have quite good paleomagnetic records, ancient North America and a piece of Africa in red in this mustard color. And what you can see is back to 540 million years ago, give or take, these continents are all moving somewhere around 10 centimeters per year or less. As soon as we cross into the Precambrian, these speeds appear to skyrocket. All the continents seem to be moving 10 times faster than what we think should be theoretically possible. So this is absolutely remarkable. Incidentally, at the same time, we have big shifts taking place in the climate system. We have a revolution taking place in the biosphere, and we have a number of very strange, very significant geochemical changes taking place at the planet's surface. So one interesting question is, if the magnetic field is doing something weird, could it also have had an impact on these other systems? Okay, so I'm intentionally going to leave you with that as a hook, because we're actually working on trying to unravel what's going on in this period right now. So we have a project called EPIC, which is dedicated to understanding the paleomagnetism from the Ediacaran. It's very generously funded by the European Research Council. And I just want to highlight the contributions and ongoing, very interesting work by these three individuals, which is why I don't want to talk about the stuff that they're developing, because I think they should be able to present their own remarkable results. This is Leandro Gaggio, who's a researcher with us, Justin Tonti-Filippini, who's a postdoc, and Yi Xue, who's a PhD candidate. Leandro and Justin are here. So please keep your eyes peeled for what they're working on and what they're up to. And as a last note, I would also point out that there's a couple of other people also in our lab group, Aniek Vanderboom and Sophia Ryan, who are also here, who are working on their own project in the Devonian, where the field appears to be doing something remarkably similar, which is particularly interesting because if we play the card that the inner core nucleated in the Ediacaran to explain all this funny business in the Ediacaran, how do we explain the Devonian? So this is an unsolved question, but hopefully between these two projects we'll have some more strong answers for you in the next round of GeoOnsdag. So, thanks.
Yes, thank you very much for this remarkable presentation. Seldom that I learned so much. So, very, very good. So, there's time for questions.
Yes, thanks, Matt. A bit to the side, because you mentioned it at the end. So how does magnetism influence climate? So both the intensity of the magnetic field, but also how it's potentially influenced during the reversals.
Yeah, I perhaps skated too quickly through that. So I wouldn't say that the climate system was potentially perturbed by the magnetic field. But the biosphere, for example, people have hypothesized that if, for example, the magnetic field went down in the Ediacaran, that the surface is now bathing in radiation. So mutation rates could go through the roof. So the reason I mentioned climate is because one of the interesting things, perhaps I could say that I don't think that the magnetic field necessarily could influence climate directly, but our understanding of the climate system is definitely influenced by paleomagnetic information, because in the Cryogenian, the period before the Ediacaran, we think that the whole planet was covered in ice. But that's largely based on paleomagnetic evidence. So if the magnetic field was doing something weird, and those relics of ice which we think were coming from the equator actually came from the poles, then the part of the foundations underpinning snowball Earth start to melt away. So I wouldn't say that the magnetic field can influence climate directly, but certainly our understanding of these massive climate changes around this time could be strongly influenced by the paleomagnetic record.
Okay, thank you. Other questions? Yes, in the back. Joe.
I'm just wondering, things seem to go strange, before 300 million years ago. Are we certain that there's no degradation in the records? Is there no change in the magnetic records that could cause that?
That's a great question. That's actually, so these are the 4 hypotheses that we are kind of working on. These are different ideas that have been put forth in the literature to explain what's going on. And one of them is exactly that maybe the data is just all messed up. In the beginning, that was the argument everyone defaulted to. The data is screwed up. But the more people looked, the more screwed up data they found, and always at the same time. So at some point, it becomes very coincidental that all the data everywhere are messed up in exactly the same way on multiple continents. So we can't entirely eliminate this possibility, and some of the records that we're looking at now are definitely partly corrupted. So part of the task is actually sifting through the stuff that's definitely been buggered, but in addition to that, there's clearly something else going on.
Okay, thank you. Yeah, there are 2 questions. First, yep. Oh, yeah, yes.
Thank you for an interesting talk. You mentioned in the beginning that you could use these magnetic fields to fingerprint layers of rocks, say sediments. Because of if you can recall that slide. That one.
Yes.
Yeah. Apparently because of the width of the black and white fields, you can match that to that horizontal bar. But wouldn't you then have to make some assumption about the rate of sedimentation?
Yes. And that can change, and that can definitely make things more complicated. So this was a very much a simplification in order to get through it in 2 minutes. But yes, there's a lot of potential problems with just blindly trying to match together magnetostratigraphic columns. So you have to be very careful to make sure that you understand if the sedimentation rate could have changed through time, what effect it would have on the widths of these different columns.
So you would have to probably get some extra dating from other sources to be sure.
Yes, so in complicated sedimentary systems, this can be nightmarish. But for example, the fact that it works so well here is already a testament to the fact that this is a very useful tool. That the reason that we know the ages of the oceans, by and large, is because of exactly this process.
Thank you.
Yes, there was one more question here.
Why does it flip?
Yeah, I was afraid someone was going to ask that question. I don't know the answer to that, and I'm afraid nobody knows the answer to that question. So the core is notoriously complicated. It has a viscosity, the outer core has a viscosity similar to that of water. So there's a lot of turbulence in the flow. So it's a very chaotic system, and it's very difficult to model. People have managed to generate simulations which are similar to the Earth where reversals are occurring. But actually digging into the details to understand exactly what is the process by which that occurs is very complicated. But the short answer is you have little eddy currents and little instabilities in the flow of the outer core that start growing a magnetic field in the opposite sense locally. And those can, if they get big enough, manage to overturn the entire system. So the system is kind of stable in both states. And because it's also chaotic on short time scales, you can manage to kick it into the other stable state. But why it happens at particular intervals and how long it's going to take until the next one and so forth, those are very difficult questions to answer.
In the mic.
Yeah. Along the same lines, I have heard that you do not need to flip the flow to flip.
No,
Yeah, and that's, I think, important to say,
Yeah.
that you do not need to flip the flow. And I think this is really fascinating, that the same flow can give the two polarities.
Yeah, the flow stays the same because of the rotation of the Earth. And there's actually very simple two-disc dynamo systems which have no fluid at all. They're just discs with some circuit set up that can also exhibit polarity reversals, with the disc continuing to spin in the same direction.
Okay, really fascinating. I have also one question, then the last you can take the last. But when it flips, how long time is it needed to flip, and is then the magnetic field gone for a period of time?
It's not gone. It becomes really complicated. Thousands of years is the easy answer. It takes thousands of years for it to flip. There have been some controversial papers suggesting that it could happen much faster in the course of a human lifetime, or even months, but those have largely been dispelled. So thousands of years is the time scale. And the magnetic field's not gone. It's weaker, and it's much more complicated. So you don't have a purely dipolar structure. You have many more magnetic poles. So if you were standing on Earth, your magnetic compass wouldn't always be pointing the same direction according to where you go at that time.
Okay, this would stop all airplanes and everything on Earth, probably. Okay, your last question, please.
Yeah. Hello, thanks, nice presentation. So I was about to ask you about something that you have already just started to speak to him, like the multipolarity. So do you have any evidence of multipolarity in the Earth, or can this very ultra low magnetic field can be related to the multipolarity?
We have a multipolar field today. It's a very small fraction of the overall field. So when I was showing you these field structures, the field doesn't look exactly like this today. And that's because we have all these other multipolar fields which are also contributing to the field. So the dipole is by far the most powerful contribution to the overall field. But we have an octopole, for example, in our field today, which is making up perhaps 5% of the overall power to the field. And those ratios may have the ratio of the octopole and the quadrupole higher order multipolar fields. The ratio of those to the dipole may have changed as a function of time. And certainly in the deeper past, before we had an inner core, and when the thermal convection was becoming more sluggish, it's very likely that we had a stronger multipolar field, which could contribute to some of the madness that we see in the paleomagnetic record.
Okay, thank you. But then we have passed 1 o'clock. Once more, thank you to Matt Domeier for this very, very nice presentations. Give him an applause.
Thanks.
And also I say thank you for attending, so many people, and hope you see you again sometimes in January or February next year.